Welcome back. In this video, we're going to look at infinite solutions. With an infinite system of equations, you'll have two lines that exist on the same line. These systems have all the same solutions, and they are infinite. These systems are called consistent or dependent equations. Let's list an example of a system that has infinite solutions, graph it, and solve by elimination and see what we get. Let's figure out some equation of a line. I'm going to pick y equals negative 2/3 x minus 2. Let's see what happens. So my y-intercept is at -2. And the equation has a rise of -2 and a run of 3. So if I connect the dots on this one, I have a line that looks something like this. The question is, what does this look like in standard form? Well, I can multiply the whole thing by 3. That will clear the denominator. That would give me 3y equals -2x minus, now 3 times -2 would be -6. Then I can bring that -2 over by adding 2x to both sides. And I would have an equation in standard form. 2x plus 3y is equal to -6. We are almost there. Now here is how you can create another equation that is exactly existing in the same space, but just looks different. This is how you can do this. You can take what you have here, you can multiply it by any number, because that's just scaling both sides of the equation. You're doing the same thing to both sides. So it's not actually changing anything, it just looks different. So let's say I multiply both sides of this equation by 2. That would give me 4x plus 6y equals -12. So here is my system. I have the first equation, which was 2x plus 3y equals -6. And the second equation, which I had, was 4x plus 6y equals -12. Now, how can we solve by elimination? That's the next question. Well, you just have to find a number that you multiply to one of the equations so that the terms are exactly the same, only opposite. So I'm going to multiply by -2 on this one, on the first one, and I should get exactly the opposite. Let's just go ahead and check. -2 times 2x is -4x. -2 times positive 3y is -6y. And -6 times -2 is positive 12. And look at that. They are exactly the same, except their signs are opposite. And if I add them together, I get 0, 0, and 0. So I get 0 equals 0. Well, that's certainly a true statement. But what if I decided I wanted to add 2 to both sides? Well, I can do that. So then I get 2 equals 2. Well, that's true. Guess what? You can do that however many times you want to, infinitely many times, and all of these statements will be true. This is why we solved by elimination and got infinite solutions. If we wanted to graph the purple equation here that I created by multiplying the first equation by 2, well, I could totally do that, but it would be right over the top of the other equation. It's right over the top of the other line. And so you have infinite solutions. And if you wanted to, you could even graph this in Desmos and see what it looks like. It's going to look pretty much like what I just sketched, but can you think of another equation of a line? And could you create two equations that are consistent or dependent systems of equations? That's what you need to think about and give it a try on your own.